Good morning. It's a pleasure to be here. Um, my presentation has a lot of animations, and we were horsing around with these computers. We never really got it perfect, so I do apologize. I think that some of these animations are not going to play the way they're supposed to. Throughout my career, whenever the subject of accommodation and presbyopia was discussed and all the treatments that we can think of, um, everybody said, well, we just don't understand the mechanism of accommodation, and then moved on. I believe we can now demonstrate to you how accommodation occurs and presbyopia with a science-based model. And we no longer need theories. There's three main theories which still drive our discussions. None of these theories is completely correct. The Helmholtz lenticular theory is largely confirmed, although there was incomplete knowledge of the zonular anatomy. Helmholtz did not know about the posterior movements of the lens or about the posterior attachments of the zonule or movements of the elastic base in the choroid. Coleman's catenary and hydraulic theory adds engineering knowledge and hydrodynamics. However, the movements of the anterior hyaloid that have now been documented demonstrate that there is vitreous support but not vitreous pressure. Vitreous is not pushing things forward. Regardless, these theories have all stimulated research, and we've benefited from all of them. Finally, Shakar's theory is based on the incorrect concept of equatorial zonules pulling the lens equator during accommodation and increasing the lens diameter. However, the lens diameter does not increase either with accommodation or age. The Shakar theory has stimulated great controversy and has also spurred the development of scleral treatments for presbyopia. However, I don't believe it's helpful to explain how scleral treatments work by using a flawed theory. Nor is it necessary to continue to confuse ourselves by trying to remember exactly what each theory is saying. When the subject is so complicated to begin with, I believe we're better off just learning the real explanation. And I hope to demonstrate to you how new knowledge of the anatomy and 21st century biometry now enables us to demonstrate accommodation. Okay, let's try that. Okay. Our understanding of the accommodative structures has shaped the theories of accommodation. Helmholtz drawings, which were based on light microscopy, are nearly correct, at least as far back as the posterior lens surface, and then he was not correct. Rowan's electron microscopy formed the basis for his own theory, as well as for Coleman's. But further study has revealed additional zonular elements, and this has filled in critical pieces of the puzzle of how accommodation occurs. So we need to reset our thinking because all the well-known theories are based on an incomplete knowledge of anatomy. This slide summarizes the understanding that we've built up and brings us up to about 10 years ago. Let's see if this video will play.
Click on it. Click on the arrow. No. Go back to the orange and click on it.
Okay, so we're going to have to skip this. This showed the UBM, which to me really opened the doors to understanding accommodation. And we know, of course, what happens to the lens in terms of the lens thickening and accommodation, and the anterior and posterior capsule steepening. We know the ciliary muscle movements, but still, even with the UBM about 10 years ago, we really didn't see what was going on posterior to the equator, and so we never really understood. Over the past several decades, the team, including Kroff, Kaufman, and Lucien Dreckel, have produced a body of work which redefines our understanding of the anatomy and biometry of the accommodative structures, and which is the basis of my model. They deserve special recognition for this advance. Their landmark 2010 study showed the three elements of vitreous zonule and provided the breakthrough which is critical to our present understanding. Their preparation of the specimens preserved the vitreous membrane and the elements of the vitreous zonule, which had been stripped away for prior scanning electron microscopy. And that included Rowan's. Rowan was one of the greatest anatomists of the 20th century, and his electron microscopy really was the textbook that we learned from. But when they prepared the specimens and put the tissue in fixative and then started to separate it for the scanner, they removed the vitreous. They removed the anterior hyaloid membrane, and they removed all of the vitreous elements of the zonule, which nobody even understood. So they were literally taking the evidence that they could have learned earlier and discarding it.
I was under the impression that zonules were a single structure. There were zonules, and that was it. There weren't different flavors. You have introduced the idea of different sorts of zonules that are not only in different anatomical positions, but really have very different functions.
So, it turns out that there are 6 zonular pathways. And these are all listed. It includes the anterior zonules, which are shown in blue, the anterior vitreous zonule in yellow, the intermediate vitreous zonule in red, the posterior vitreous zonule shown in gray. That's this element, which we'll talk about. That's the posterior vitreous zonule. There's also the pars plana zonule shown in green, and the very recently discovered posterior insertion zone to lens equator zonule, which is shown in purple. In order to demonstrate these fibers and their role in accommodation, I have created a computer animated model. Models are of central importance to conceptual change in science. The double helix is one of the best examples. In 1953, Watson and Crick produced a model of DNA structure and function. But they didn't discover DNA. It was discovered in the 1860s by a Swiss chemist, and 90 years of research preceded their building their model. But then look what happened. All the mysteries of genetics have unfolded. So who knows? A model may help us finally unwind the secrets of accommodation. In producing the model, the most up-to-date research in accommodative science was critically analyzed and incorporated, particularly the new knowledge of the anatomy of the zonule and the extralenticular structures. The form of the model is based on the horizontal plane, as seen in the video UBM, and the scale is correlated with the latest biometry. After the model is constructed in accommodation and in disaccommodation, then Autodesk Maya is able to create the animation, and the final details are generated by Adobe After Effects. In 2011, I produced the first computer-animated model of accommodation and developed the theory of reciprocal zonular action of the anterior and posterior zonules. The theory of reciprocal zonular action was developed with model-based reasoning as follows. During ciliary muscle contraction, the anterior zonule fibers lose tension while the posterior zonules stretch. During ciliary muscle relaxation, the posterior zonular fibers lose tension as the lens is pulled back by the increasing tension of the anterior zonular fibers. After the first model was built, there was more research and better biometry, and there was even another zonular fiber described. So I went back to the drawing board and used these studies. The advanced biometry with UBM and OCT has really enabled us, given us an ideal data set to build the model to scale. Two fantastic studies published in 2013 document quantification of age-related and per diopter accommodative changes in the emmetropic human eye. That's the Ridgedale study. And as well, there are critical biometric measures of extralenticular structures provided in the Croft study. That enabled me to size the elements in the model and to develop a much more anatomically accurate animation. I now present version 2.0, which includes new knowledge of the anatomy and accommodative movements of the ocular structures, as well as incorporating the latest biometry. The normal adult model is based on a 25-year-old human eye with maximum accommodation of 8 diopters. The model is based on anatomy, biometry, endoscopy, and video UBM. It is not based on theory. And the findings are based on model-based cognitive reasoning. Well, we got something screwy on this slide. It's a little bit compressed horizontally. The main message from the model is that the mechanism of accommodation is related to reciprocal zonular action. Ciliary muscle contraction results in release of tension on the anterior zonule, allowing the lens to round up due to the intrinsic elasticity of the lens and the lens capsule. At the same time, the elastic foundation in the choroid stretches. When the ciliary muscle relaxes, The elastic tension in the choroid pulls the ciliary muscle posteriorly, resulting in tension on anterior zonules to flatten the lens and disaccommodation. Muscle movements throughout the body involve sets of agonist and antagonist muscles to achieve back and forth movement. In the case of accommodation, there's only one muscle or set of muscles. The ciliary muscle has three separate divisions. The ciliary muscle is the only muscle moving, and it acts by releasing tension on the lens during accommodation while stretching the elastic foundation in the choroid to store energy for disaccommodation. Thus, the accommodative system functions with one muscle providing tension and release to two opposing elastic structures. During disaccommodation, the elastic tension in the choroid pulls the posterior zonule and the ciliary muscle back to the resting position. And since this physiology is so unique, the mechanism of accommodation was elusive for over 200 years. I'd like to see a better name than Brooks Elastic Foundation in the choroid, because we all understand lens, ciliary muscle, but we need to know what's the other part of it that's pulling and stretching and allowing the mechanism to occur. So I'd rather see us come up with a better name for that elastic girdle that's really surrounding the globe and is intimately involved with the accommodative movement. Okay, here in a rhesus monkey eye, we can see the reciprocal movement of the ciliary muscle pulling the posterior zonules and the elastic extension in the choroid, as well as the return of the ciliary muscle during disaccommodation. Notice the region where the posterior zonules pull the choroid and the overlying retina. See if we can get that to play again. Sorry. But here in the pars plana, the retina is being pulled forward, and took a long time for people to really believe that that was occurring. So, after analyzing the model, I've divided the zonular architecture into three groups based on structure and function. Here we see the anterior zonules losing tension as the posterior zonules are put on stretch. I guess we get to see an animation for a few seconds. That's it. The anterior zonules are the first division of the zonular architecture, and the function is tension and release on the lens capsule. The anterior zonule can be divided into two or three subdivisions. There are anterior and posterior divisions of the anterior zonules, or they're called the anterior and posterior tines, T-I-N-E-S. And there's also equatorial fibers, which have been debated whether they exist or they don't, but they are there. Not always, but many times equatorial zonules are seen. In addition, there are specialized proprioceptive fibers, which are called the most anterior zonule. And this creates a neurologic feedback loop to enable fine focus. We also know that the anterior zonule moves forward with age and with the thickening of the lens. The second division of the zonules, which is the crossing zonules, which along with the Weiger ligament cradle, shape, and stabilize the lens. The crossing zonules include two pathways. The anterior vitreous zonule, shown in yellow, and the posterior insertion zone to lens equator zonule, shown in purple. The crossing zonules prevent outside forces from displacing the lens. Think of a skier going down the mountain hitting the moguls. Something's got to keep the lens in the right place, and that's what these structures are doing. The crossing zonules prevent outside forces from displacing the lens, while the anterior and posterior zonules work reciprocally to keep focused vision. And that really, in a nutshell, is what is happening in accommodation. The Weiger ligament I point out because it's very important. Notice the null point of anterior and posterior lens movement is exactly where the Weiger ligament is located. Now, it is known that the lens equator and anterior capsule move anteriorly during accommodation, while the posterior lens capsule moves posteriorly. The Weiger ligament encompasses the null point of the lens where there is no anterior-posterior displacement during the accommodative cycle. This is the ideal location for supporting the lens. Both the cradle-like shape, notable in the model, and the null point location of the Weiger ligament suggest an important function for a structure which heretofore has received little attention in accommodative science. The primary function of these structures is to support the lens. There is a secondary function of the anterior vitreous zonule. I think our animation plays a couple seconds then stops, but with this model, if you looked at the yellow zonule, the ciliary muscle contraction causes an angular rotation of the anterior vitreous zonule, which I believe is the secondary function of that zonule, and very likely helps to shape the lens as it rounds up during accommodation. The posterior insertion zone to lens equator zonule prevents anterior displacement of the lens by outside forces. The location of the PIZLE zonule, which stretches around the peripheral hyaloid membrane, further suggests that this structure provides support to the vitreous, preventing the vitreous from moving anteriorly where it would mess up the whole zonular system. The ciliary muscle radial fibers insert into the scleral spur and effectively suspend the lens in the scaffolding created by the Weiger ligament and the anterior vitreous zonule. Thus, the limbus is really the origin of the suspensory structures of the lens, and these support the lens while the anterior and posterior zonules reciprocally act to focus. The posterior zonules include three pathways: the intermediate vitreous zonule in red, the posterior vitreous zonule in white, and the pars plana zonule in green. The posterior vitreous zonule is a sponge-like structure at the vitreous base with obliquely crossing fibers capable of dampening the forces of accommodation and preventing trauma to the peripheral retina. The function of the posterior group is to transfer tension and release from the ciliary muscle to the elastic foundation in the choroid. The posterior zonules anchor the ciliary body and extend posteriorly at the posterior insertion zone to attach to the elastic Brooks membrane in the choroid. When the ciliary muscle contracts, the posterior zonules attached to the elastic elements in the choroid stretch and store energy for disaccommodation. When the ciliary muscle relaxes, the elastic fibers of the choroid pull the posterior zonules and the ciliary body posteriorly, and as the ciliary body moves posteriorly, the anterior zonules stretch and flatten the lens. The hydrodynamics indicate that the vitreous space is passive. Internal movements of the vitreous body are related to the surrounding structures of the lens, the aqueous in the posterior chamber, and the uveal tract. Those are what's causing movements inside the vitreous. The motion of the anterior hyaloid membrane is especially important because with the lens rounding and accommodation, the aqueous moves peripherally, and the hydrostatic pressure anterior to the vitreous space overcomes the hydrostatic pressure inside the vitreous space. Along with the documented movement inside the vitreous cavity, this is strong evidence that the vitreous provides passive support, but not pressure pushing the lens forward. And these movements were all documented by injecting triamcinolone into the monkey eye and then documenting the movement of the aqueous as well as the vitreous movements. The movement of the anterior hyaloid is shown here and provides evidence that the hydrostatic pressure in the aqueous space is greater than that in the vitreous space. Otherwise, this anterior hyaloid would not bow backwards. There's more pressure in front than there is in back. This is strong evidence that Coleman's theory of vitreous pressure is not correct. There is vitreous support, but not vitreous pressure. Through the accommodative cycle, aqueous production and drainage are in equilibrium. However, during ciliary muscle contraction, there is a relative pupillary block as the lens moves forward and rounds up. The anterior chamber shallows centrally and deepens peripherally at the same time that traction on the scleral spur stretches the trabecular meshwork and enhances aqueous outflow. This drives the pulsatile outflow of aqueous. In the posterior aqueous space, the iris moves posteriorly, which pushes the aqueous in the posterior chamber posteriorly, where the added volume of fluid helps the lens round up and the anterior hyaloid to move posteriorly. So the lens is rounding up in part because of the reduced tension of the anterior zonule, in part because of the hydrostatic pressure of the aqueous being pushed peripherally and inferiorly, and also because of the angular movement of the anterior vitreous zonule. The reduction of accommodative movement with age may contribute to reduced outflow with age and is clearly related to the development of glaucoma. The vitreous body is a transparent connective tissue with viscoelastic properties where movements external to the vitreous cause internal movement within the vitreous. During accommodation, the posterior movement of the lens axially results in posterior flow of vitreous behind the lens. At the same time, the most peripheral anterior hyaloid membrane is being pulled anteriorly by the intermediate vitreous membrane, which actually inserts into the peripheral hyaloid membrane, and it pulls it up. The presence of cisterns within the vitreous could channel the flow within the vitreous and facilitate the back and forth movements of the lens and uveal tissues. However, it is unclear whether movement within the vitreous has an effect on the surrounding structures, and this is an area where we need some more research. The Croft team also demonstrated scleral movement during accommodation due to traction of the ciliary muscle on the scleral spur. And the top part will show you the relaxed, disaccommodated eye. Sorry, go backwards here. The sclera actually has a little notch that shows up medially, and as we get older, it tends to sag, and there's a kind of a depressed area medially where the sclera is coming in, and this this may actually explain in part why the circumlental space is narrowing with age, because the scleral shell is actually changing shape. Scleral treatments which reduce the rigidity of the sclera or change the geometry of the posterior chamber may be an effective treatment for presbyopia. In presbyopia, the model demonstrates proportionate reductions in lenticular accommodation, ciliary apex movement, and movement of the ora serrata. This was a key finding of the Richdale study, and it's fascinating that the movement of the ora serrata, the ciliary muscle apex, and the lens thickening, they're all proportionate. And presbyopia, of course, occurs to the stiffening of all accommodative elements, especially the elastic base in the choroid. And I think that data from Richdale proves that it's not the lens that is hardening and everything else just falling into place. It's the whole eye that's really getting rigid, losing elasticity, and the viscoelastic elements are just not cooperating anymore. Anterior movement of the ciliary muscle is restricted by the posterior loss of elasticity in Brooks membrane, and therefore treatments which can increase the compliance of the zonular system may be one answer to the treatment protocol. Here, the older monkey eye demonstrates the loss of anterior movement and narrowing of the circumlental space seen in presbyopia. I don't think we can get this to play, but of course, this is related to the theories about the etiology of presbyopia, and certainly there is a mechanical change that reduces the effectiveness of the accommodative mechanism. been well shown that the ciliary muscle maintains its ability to contract and to move centripetally. So it's the lens as well as the extralenticular fibers and the elastic base in the choroid that are responsible for presbyopia. It's encouraging that recent discoveries regarding zonular structure have been consistent with this model and have reinforced its findings. These studies include further documentation of the newly discovered posterior insertion zone to lens equator zonule and further findings regarding age-related posterior ciliary muscle restriction, which contributes to presbyopia. The take-home messages are listed. The mechanism of action is reciprocal zonular action. There is vitreous support, but not vitreous pressure. Zonular architecture is divided into 3 divisions based on structure and function, and the important support structure of Weiger ligament is shown. Presbyopia results from loss of elasticity of both lens and extralenticular structures, as well as the growth of the lens. Hopefully, now that we can understand accommodation and presbyopia, we will soon figure out more effective treatments. Thank you all very much. I'll be happy to share the file, the animated file, to anybody. Just send me your request on my email. Thank you very much.